esse contexto que o Ciro trouxe para a gente, que eu aprendi nesses meus 8 meses de iFood, é muito legal, mas me gerou uma pergunta, né, para mim mesmo, que era o que outras empresas, outros desenvolvedores estavam fazendo com essa linguagem aqui no Brasil. Não lá fora, aqui no Brasil. E foi aí que nasceu realmente a ideia de ter esse momento que a gente está tendo aqui. E aí, para começar esse dia, eu achei nada mais justo do que a gente começar falando sobre o que é, onde está, para onde vai e por que os desenvolvedores curtem tanto essa linguagem. E aí, para trazer essa mensagem para a gente, eu convidei o Niko, que eu vou chamar para a tela aqui rapidinho, daqui a pouco, para contar um pouquinho da experiência que ele tem. Niko é um cara, para quem não conhece, tá trabalhando com Rust desde o início. Então, pensa num cara que ajudou a criar o tal do borrow checker. Talvez vocês vão aprender, quem não ouviu falar isso, vai ouvir hoje falar. Então, é um cara super estratégico para a gente, é literalmente uma honra ter ele aqui para compartilhar. E aí, como eu falei, para a galera online, a gente vai jogar um link nos comentários. Deve ter chegado no seu e-mail também, com os dados de acesso para o Zoom. Então, se você quiser ouvir a palestra em áudio original em inglês, você pode ficar no YouTube, onde você está agora, tranquilo. Mas se você quiser ouvir a palestra com tradução simultânea, a gente vai jogar no chat um link, e também deve ter chegado no seu e-mail, se a automação funcionou certo, o link para você acessar o Zoom, e lá você vai conseguir ouvir em português. Beleza? Galera, vocês aqui, eu acho que quem precisa já está com o fone. Bora chamar o Niko aqui. Hey, Niko, are you there? Hey, I see you. How are you?
Oi, pessoal.
Hello, can you hear me?
Você me ouve, Niko? Sim, te ouço bem.
Aqui na sala. Just a second.
Só um minutinho.
Because we hear you in Portuguese over here. And he was supposed to be in English. You have a funny voice in Portuguese.
I sound a bit different, huh?
Oh, there you are. All
okay,
right.
Excellent.
All right, now it's you. Hey, thanks for being here. It's a pleasure.
Thanks for having me.
Yeah, for sure. And how are you today? I know it's a Saturday. You have this weird guy from Brazil saying, hey, come talk to us. So how are you?
So, to be honest, I'm feeling grateful because I came down with COVID last week. That's not why I'm grateful. I'm grateful that I'm feeling well enough to come and do this talk with you today because it's been a little rough, but I'm doing pretty good. I'm on the mend.
All right, it's nice. I don't know if you can see it. Maybe you can see on YouTube, but we have a packed house. We have a lot of people online, so you're gonna be famous if you more than you already were.
That's pretty.
And before we get going, just tell us a little bit about your background and your involvement with Rust and Rust community in general.
Sure. Well, so I started in Rust in 2011. That's about, I usually say about 10 years, but I guess it's going on 11 years now. I came to Rust, I did a PhD before in language design, and so Rust was kind of like the perfect job for me. And I started at Mozilla working on it. And I've been doing it ever since. It's been great. I mean, it's kind of the work I always wanted to do, helping give people a tool to build really cool, things that they want to build. That's what I always wanted to do. So that's been my journey here, I guess.
Your calling, per se.
Yes.
All right. And what do you do today?
Well, so I'm a senior principal engineer at AWS. Most of the time I work on Rust still. So I'm the co-lead of the language design team. So I work on, deciding what things we're going to add, what we're going to change in the language as it goes forward. And I work a lot on the compiler as well and how it's implemented itself, especially the type system and the trait system.
Nice. All very fancy stuff. And I was telling everybody here that would be a great idea for us to start talking about what it is, where it's going, and why developers love this thing so much. So, and maybe if we have the time, talk a little bit about some of the challenges that you've seen. I know you go around the world talking to people, so if you could share that with us would also be great. Let's put his slides on the screen. With that, I'm going to give everybody here a quick message in Portuguese, and then the floor is yours, all right?
Oh, okay, sounds good.
Pessoal, online, se você está aí com o link, já está no Zoom, beleza? Se não, corre para lá, ainda dá tempo. Pessoal, aqui tem algum problema, se precisar, ali no cantinho, vocês conseguem pegar o microfone, beleza? Vou colocar o slide dele lá. All right, Niko, your slide is up. I'm going to be here with you throughout the whole thing. If you need anything, just let me know. The floor is yours, and take it over.
All right, thanks very much. So
Hey, wait.
Oh, okay.
Clap, everybody, clap.
I could almost hear that.
All right, now you can go.
Okay. Yeah, so we kind of covered this already, but my name is Nicholas Matsakis. I'm a senior principal engineer at AWS, and I work mostly on the Rust language design. But I'm here to talk to you about where Rust is, how it's grown over the years, and what I think are our big challenges and the things we ought to be focusing on now so we can keep growing. So one of the things that's been happening, and it's been amazing to watch it happen, is Rust has just started showing up all over the place, right? When we first started working on Rust, I remember saying, I think I'll be happy if someday I hear about somebody using Rust to do something cool and I didn't know about it beforehand, right? Well, that day is like, we blew past that 10 years ago. Now I hear all the time about new companies picking up Rust, right? So this slide just shows the foundation sponsors. We launched a Rust Foundation a few years ago. I'll talk about it a bit more later. And these are just the sponsors, right? There are, of course, tons of companies out there, especially startups all over the world, including Brazil, it turns out, who are making great use of Rust. And so that's really great. And people are using Rust, for all kinds of things, but I think I would characterize Rust's natural home as the sort of foundational layer of stuff people build, right? And so that includes things like cloud providers. We have headlines like AWS and Azure and other folks using Rust. We at AWS, we use it to build S3, build CloudFront, build these foundational services that other people build their stuff on top of. That includes things like operating system kernels. We've seen headlines lately that Rust will be, you'll be able to write Rust drivers in the Linux kernel. There's some experiments in Microsoft. I don't know the status of those, but that kind of low-level layer. It includes things like embedded systems or Internet of Things, IoT, where you have little computers all over the place, automotive, stuff like that. So it includes these kind of, I don't know what's the right word for it, hardcore things, but it also includes a lot of stuff that's much more common. Like if you implement a web service that moves a lot of traffic and has to be fast, Rust is a great choice. Maybe it takes a lot of orders from around the country and has to make sure they get delivered on time. Or if you're building a mobile app and you have some logic that you'd like to share across Android, iOS, maybe the web, and you'd like to have a single source code that can be compiled and run on each of those, Rust can do that too, and a lot of people use it for that. And one trend I've started to see, notice lately is people building development tools in Rust, like ESBuild, I think it's ESBuild, uses Rust as part of their linting and compilation toolchain, and there's other kind of linters implemented in Rust, and the ripgrep and so forth. So these are all different versions and varieties of the sort of foundation, right? It's the foundation of whatever it is that you're doing. That's where I think Rust has its natural home. So the question is, why work on Rust? In other words, I often get asked, you've been working on Rust for 10 years, like, doesn't it get old? Is it just that you hate garbage collectors? Is that what keeps you doing it for so long? no, I don't hate garbage collectors. In fact, I think they're pretty cool, but we do have a tendency to kind of make a mess more often than not. And what I actually like, and I said this earlier, but I like building Rust because I like seeing people build things, all right, and helping them do that. And Rust is a great tool for that. So our slogan here, this is from our webpage, a language empowering everyone to build reliable and efficient software, right? And there's a part of that I want to emphasize, which is empowering everyone, because I think there's a reputation in the olden days, let's say, or one that Rust is trying to change, that if you wanted to work on those foundational layers, you had to be a sort of systems programming wizard, right? If you wanted to get, if you had a part of your system that maybe you built it in Ruby or in Python or something, and it was running too slow, you could convert it to C and C++, but you'd have to hire some sort of different kind of engineers with a lot more time and investment to make it actually work. So one of the goals for Rust is to broaden that pool and make it so that anybody can work on those foundational layers wherever they might show up, right? Because sometimes I'm pretty sure that they're showing up also in the stuff you work on. So I've noticed a trend, and I didn't know you were gonna have this operations engineer speaking this morning, but it was perfect because I've noticed this sort of trend in how Rust adoption plays out. That people come to Rust initially because they have some service or some part of their program or something that's running too slowly, or they have a real need for performance. And so they're willing to take the gamble and put a little effort into learning something new in order to get it, right? And a good example comes from this 2020 blog post from Discord, where they switched talking about why they switched some of their stuff from Go to Rust. And in their case, they had a service that tracked, I think it was the read state. In other words, is a message read or unread for every message, right? And it's pretty important that it be fast. And they were having problems. It was implemented in Go. They were having problems. You can see here in this little chart that every once in a while, the garbage collector would come in and their latency would spike, right? And they couldn't get rid of it, whatever they did. And now, in all fairness, I should say this was 2 years ago. Go has a new garbage collector. I don't know what these charts would look like now, but I can say that problems like these are very common, no matter what language, no matter what version you're using. There's usually some kind of rough edge, right? And so they converted it from Go into Rust, and they saw this. And you may not have noticed, but there's a little blue flat line along the bottom. That was the performance they got when they converted from Go into Rust, right? And they were really happy about that. So that's kind of how it starts. But then 2 things happened. First, once they had rewritten it in Rust, they felt they had a lot more confidence and ability to make further changes, right? And they went and made other optimizations that they'd always wanted to do, but they couldn't do before for whatever reason. And now they went from microseconds to milliseconds, right? So they got orders of magnitude improvement. And they kept on using it. They went on and they stayed and started using it in other parts of their system because they found that, actually the borrow checker and the type safety made it easier to refactor code, as it says right here. Maintaining their code was actually easier than it had been before. They could move faster. And that's not just Discord, right? That's a story I hear quite a lot. We just heard it this morning, actually. And here's a recent blog post from pinecone.io. They used Python and C++. They converted both of those into Rust. They found developer velocity improved dramatically, while real-time operational events dropped to 0, right? So they didn't have people getting paged in the middle of the night because of bugs. Cultivate HQ had a quote about moving forward with confidence, curiosity, and protection. These are kind of this is the feeling we want to engender and that I'm so excited about. This feeling of, excuse me, the feeling of understanding your code and being able to do and build the things you wanted to build, just the way you wanted it to work. So that is kind of the pattern, right? People start with some performance critical piece of infrastructure. They get lured in by the performance, but then they find actually it's more maintainable, right? Once they've gotten over the hump and invested the time to learn Rust, and they start using Rust for more and more and more things. So what is it that makes Rust feel so productive? Like, what is it that makes them stay and move faster? And I think it's a lot of things. It's not any one thing. A big part of it is tooling. Right? We've invested a lot in quality tooling for Rust. So we have Cargo and our package manager, and Crates.io is one of the best, in my opinion. Makes it very easy to add dependencies, use people's libraries. We've put a lot of work into our error messages. We don't just want to tell you that there's a problem. We want to help you understand what that problem is, give you suggestions for how to fix it. And I'll talk a little bit more about that, about ways I think we can take that to another level. I mean, it's interesting, error messages, they're often an afterthought, but I think almost every, if not every conversation I have with a Rust engineer, or someone using Rust, will bring up the error messages and how helpful they've been in learning Rust. So I think it's a really powerful tool to use. And there's also just a lot of great libraries to use. I think Rust is a language where you can build really efficient libraries, which then allow people to build really efficient things that use those libraries, right? And powerful things. So, I mean, one of my favorite examples, VS Code is using the Rust regular expression engine, right? To do, if you search across files, that uses ripgrep, which is written in Rust. And interestingly, I think a key part of how Rust is so productive is our really strict type system. And that's a little counterintuitive, actually, if you think about it. Because I think most people, when they think about a type system or safety, words like that, they don't think of productivity. They think more like bureaucracy or maybe spinach, right? The food that you should eat because it's good for you, but you don't really want to eat it. Well, I agree. A type system is a lot like spinach, but it's not this kind of spinach. It's more like Popeye spinach. The kind, I hope everybody knows Popeye, but the kind that you eat and then it makes you super strong and you can get all these things done that you weren't able to get done before. And I think the reason for that is simply this, that if you don't have a strong type system or a focus on reliability, it's really easy to make this kind of beautiful looking program where you set everything up and it seems like it's all fitting together and you're having a great time building it. But as soon as you start to run it, there's just problem after problem after problem, right? And it's hard to get everything to work. And then what's worse, usually maybe the first version works okay, but then you want to make a change, right? And you have to maintain all the invariants and all the connections, and you don't have any support to do that. So with a type system, it's different. I mean, first of all, there's just a lot of bugs that you can't have. So it's not just about garbage collection. We talk about garbage collection a lot. Rust type system rules out seg faults and double freeze. So those are the kind of bugs that you would hit in C code, or C and C++, and the garbage collector would sort of protect you from. But we also don't allow null pointer exceptions. We don't allow data races. So if you've written Java code, you've probably hit null pointer exceptions. You've probably, if you tried to run in threads, you've probably hit data races, or maybe you didn't know it, but you have them waiting and lurking for you. Those things, just won't compile in Rust, right? But it goes beyond that kind of thing. It's also, we kind of geared for reliability wherever we could, right? So we're kind of aggressive about our default warnings, for example. We'll warn you if we see dead code that can't run, because why was it there in the first place? We'll warn about variables that aren't read. These warnings, all I will say is every single one of these warnings I listed here has caught for me several bugs up ahead of time where I say, wait, that code shouldn't be dead. Why is it dead? Oh, look, I have a missing, I screwed something up. And we even have a tool called Clippy. You can click here if you have the links, or you can find it online, that gives you even more warnings, and it will help you learn Rust. So it'll find things that you've done that are not idiomatic, for example, or not the most efficient formulation, and suggest that you change it. That's really nice when you're learning, especially. So I recommend everyone use that. But the goal is, wherever possible, to help you identify something that seems suspicious and fix it before you run into a problem at runtime, right? And that does mean more investment up front. You've got to learn how everything works. You've got to work through all these warnings. But the goal is that once you get it up and going, it just goes. Now, that's the good part. That's when everything's working right, it feels like this. But there's another side to it, right? There's a little full disclosure, which is sometimes, well, the type system is great, but it takes a while to learn it, and it's not a great fit for everything. Sometimes you have to kind of work around the type system rather than benefit from it, right? And my experience is it takes about 3 to 6 months for people to really get productive in Rust. I'm not sure about that number. We heard a different one this morning, and I hear lower estimates and occasionally higher. But regardless, it's an investment of time. And it can be really frustrating because you have to kind of, one part of the way that Rust works is quite different from other languages. And so you have these patterns that you're trying to apply that you know from Java or you know from somewhere else. And they don't really work that well in Rust. You have to learn a new way of doing things. What usually happens is that at some point, you kind of turn the corner and suddenly you're not really sure why it was hard in the first place. It seems natural. You've just figured out the way that you should structure a Rust program and you're able to do that. So I've heard this slogan at some point that I really love that I thought captured this experience. It says, Rust, the language where you get the hangover first. So a hangover, if you're not familiar with it, that's what you feel after you've been out drinking all night. So, normally when you go out drinking, everything feels great the night before. You're having a good time. And then the next morning, you're like, oh my God, what was I doing? Well, Rust, it's kind of the opposite. You're struggling for a while, trying to put things together, and then it works great. And, if you have to pick, I think that's the better one. But what is our challenge? What are we trying to do now as we continue to evolve Rust? I think we want to keep the benefits, but we want to lose the hangover, at least as much as we can. I mean, the reality is some of those benefits, right? This emphasis I've been making on reliability and efficiency, some of that, it's just harder to do, to build software that's reliable and efficient. It's going to take longer. It's going to require some upfront investment. But that doesn't mean there's not a lot of opportunity to make things a lot easier and smoother. I think another big challenge that I've noticed is being bold. Rust is going on 10 years. I've been working on Rust 10 years now. Rust has been stable. We've hit 1.0 in 2015, so that's 7 years ago. And it gets harder and harder to make big changes, as it should be. There's a slogan in the Haskell programming language, if you've heard of it. It's a great functional programming language out of academia, but it's also seeing some usage here and there. And they say that their goal is to avoid success at all costs, right? And the reason is because they want the freedom to keep innovating and changing and reinventing the language. So Rust has achieved success, and we always wanted it, but I still want us to soar, right? And I think we have to keep in mind that requires being bold and looking, and just because something seems really hard to do or because we've always done it that way, it doesn't mean we have to keep doing it. So I'm going to give up a few examples in this talk of some hard problems that are either just really hard to find a good answer or controversial, but I think they could have a real impact. So let's turn to where Rust is going. And I have to make a confession. I don't know exactly what Rust in 2024 is going to be like. I picked that year because of the Rust edition system. Every 3 years, we release a new edition, which lets us make some changes to the language. It's kind of this opt-in system so that you can opt into using the newest version. Your code still interoperates with code from the older versions. So no one else you don't ever have to change to adopt the new conventions, but if you do so, you'll get some benefits. Usually we have tooling to help you transition. So, and I don't know exactly what's going to happen in Rust in 2024. There's a couple reasons. One of them is, everything takes longer and it's hard to predict the future. Engineering estimates are always wrong. But the other one is that Rust is a community-led project, and I'm just one person. And so we have a number of teams in our open source org, each of which owns their own distinct areas. There's a lot of things going on. I can't keep up with all of it. And also, I'm sure that in between this talk and 2024, people are going to have a lot of new and exciting ideas, and we're going to jump on them. But with that caveat aside, let me tell you some highlights of what I think for sure we will be doing. And these are some things I'm particularly excited about personally. I'm going to start with async Rust. So async Rust is we first released async await around the end of 2018, early 2019, and it's basically a way to run a lot of network connections concurrently very efficiently. You're probably familiar with it from JavaScript or from C# or other languages that have a similar feature. So we released our version, and it's been really successful. Right? This is a huge growth area for Rust. I don't know whether iFood uses async await, but I bet they do. And I can tell you for sure it's widely used at AWS. Now, the thing is, what we shipped was a kind of MVP, a minimum viable product. There's a lot of things that I think it should work in the language with async await, but don't. To see what I mean, take a look at this trait. So a trait in Rust, this is a kind of interface, and this is the iterator trait. It models a sequence of items that you can get one after another, right? This is a sequential trait. This is not async. So you can't use it with await. But the idea is you have this associated type that tells you the kind of item that's going to be yielded up by this iterator. And then you have this method next that you can call to say, give me the next item in the sequence. So like I said, this is a sequential iterator. It doesn't support async await. So here's a question. What does the async version of this iterator trait look like? Right? Surely there is one. Well, no, that's a trick question. We don't have an async version of the iterator trait, at least not a standard one in the standard library that everyone agrees on. And that's because we don't support async functions in traits. There's a few, this has been a long journey, but if you want to use async functions in traits, so if you want to have an interface that includes an async function, you have to use this macro, async trait. That comes from the standard library, sorry, not from the standard library. That comes from crates.io. It's a great crate, written by David Tolnay. It's very useful and widely used, but it's not built into the language, and it doesn't work as efficiently as something built into the language could work. And that's true for a lot of things. This is kind of part of your experience if you're using async Rust now, is the core fundamentals are really strong. And if you know the right set of tools from the ecosystem to use at each place, you can be really productive, but you have to learn that right set of tools. And that's a learning curve gap and a frustration thing, especially when you're first learning, right? So that's sort of what happens at the language level. There's a few other challenges around async Rust that I see. Like we have these really great networking runtimes. So in Rust, in the standard library, if you want to write to a network socket using async IO, we don't support that. You have to get that out from crates.io. And that's because it's a fairly complex task and there's a lot of trade-offs. So the plus side of this is there's all these great crates that optimize in different ways. One of my favorites, well, Tokyo is sort of the most widely used. It's great for normal servers and things like that. And then Embassy is one of my favorite counterpoints because it actually works on embedded nodes that don't even have an operating system. So we have this wide range of things. But the problem is, what about if you're just getting started? Which one do you use? How do we write all our documentation? That's a bit of a challenge. So we need some kind of mechanism for interop, right? So that you can, well, in particular, it'd be nice if you could write libraries that didn't really care which runtime their client was using, that they would just work transparently. And that's not possible today. That's partly because those libraries would need traits, and we set up here, we didn't have traits. So there's a kind of cascade. And finally, we could use much better tooling. I emphasize the importance of tooling. So I think these are some of the challenges, or the strengths, but also the challenges that we see around async Rust at this moment in time. And I should add, when I said that it takes 3 to 6 months for people to learn Rust, part of it is I was including things like this, right? You might learn the basic language very quickly, but to really get up to speed in your particular area, you might find, oh, I have to learn find these ecosystem crates and learn how they work and so forth. So what can we be in a few years? Well, first of all, we can support async functions and traits. We're working on that. We're actually getting close, I think. It's been a long journey. It's been a tricky design. And that will enable us to have a much richer ecosystem. We're working now on what sort of in parallel, we're anticipating that we have async functions and traits and working to design what will the traits be that will enable us to interoperate between runtimes. And there's really exciting work like Tokyo Console. It's not part of the Rust org per se, but building cool new tooling that lets you see all the things that are going on and debug problems. So I think in a few years, the async Rust story is going to be much better. But I talked about being bold, right? And I think there's a problem looming on the horizon that we don't have a great plan for yet, and that we need to think about how to solve if we want to solve it. Right? So I mentioned async functions and traits. So the idea would be, well, we should be able to write an async iterator like this, and we should be able to say that it's async. That should work, and I think we will make that work. But here's the question. Do we want to have an async version of every trait? Which traits, like, we now, does that mean we have to go through and make a separate copy of the standard library? That's kind of a pain for us on the one hand, because we have so many traits, but also a pain for users. You know, let me show you. So this is some standard Rust doing a sequential iterator. So this is, if you're not familiar with Rust, this is kind of walking down a sequence. Well, actually, I'll walk through it. Right, so we have an array of data, and when we call x.iter, we get back an iterator. So we're going to go over each piece of data one by one. When we call filter, we're going to run this test. Is it valid? And if it's not valid, we'll drop it out of the sequence. Then we're going to apply this mapping operation. So we're going to call intermediate result to get an intermediate result. And then now we have a sequence of intermediate results. And then we'll call max to pick the maximum one. And so this is perfectly valid Rust code. But if you wanted to put in an await in here, you know, it would be nice if that would work. But even if we had an async iterator trait, you still wouldn't be able to write await here because you're still in a sequential iterator. You'd probably have to go and change something else. Like maybe you have to change .iter to .async iter, you know, and actually we already have this problem today, even without async await, because we have the way Rust does error handling is with this question mark operator, which kind of propagates an error. Normally it propagates it to the enclosing function. But when you're in an iterator, it would be nice if this question mark could propagate out of the function find element. But in fact, it only propagates out of the map, doesn't quite do what you want. So we already start to have these problems where you want to have many different varieties of iterator that kind of compose, right? And that multiplies times every trait. Now, this is not a problem unique to Rust. If you've used other languages, it's often called the color problem from this famous and rather entertaining blog post by Bob Nystrom. And basically it's saying in languages, you often end up with more than one version of the same basic thing. It would be nice if we could do better though, right? I think it's not fatal if we end up here, but I'm curious if we can do better. And so there's an effort going on, an experimental initiative called keyword generics. And the idea is you have this async keyword. What if you could be generic over whether you are async, right? And there are other such keywords like const, which allows us to evaluate compilation time we might like to be generic over. So this is pretty exciting. We'll see where it goes. If it works out, it's going to make writing async Rust code much more natural. All right, so that's one place I think we're going. Another is improvements to the core of Rust. So this one is harder to summarize. I won't go into a ton of detail, but there's a key concept in my mind here, which is inherent versus accidental complexity. Right? Inherent complexity is complexity that's tied to the problem that you're trying to solve, because some problems are just hard and it's not really Rust's fault, right? And this is where I said earlier, like when we try to get rid of the hangover from Rust, we're only able to be so successful because we're trying to help you build more reliable software, and more reliable software is just harder to build. That's the inherent complexity. But the accidental complexity comes from the way that you're trying to solve it, right? Some tools are hard to use, even on top of the problem being hard. And so we want to try to reduce and get rid of that accidental complexity as much as we can. Let me illustrate for you this concept with a code example. This is a bit of Rust code called get lazy. Given a list, it returns a mutable reference to the first item. And if the list is empty, it pushes a dummy item and then returns that dummy item. Right. So there's a lot of Rust code in this example. You don't have to understand everything, but right here you see where the pointer is pointing. That's the option type. That's how we do null pointers in Rust, actually, or what we sort of the equivalent of null pointers. Instead of saying something is null, you say that it's an optional thing, and it's checked. If it's optional, we have to check whether it's present or not. We won't let you just use it and then get a null pointer exception. So this problem that something might or might not be there, that's inherent complexity. The fact that we use options to solve it and that we have some syntax and matching for working against those options, that's accidental, right? That's part of how Rust is designed. There are other ways to solve it that could be simpler, could be more complex, and so forth, right? So I happen to think options are pretty okay, although we have some improvements underway. But another piece of this example is this and mute reference, ampersand mute, right? In Rust, when you take in an argument, an ampersand mute reference means I have unique access to this vector for as long as my function runs. I can change this vector and no other function can read it or change it, right? It's unique to get lazy. And this concept, I actually think this is sort of inherent complexity. I think this is the key part of Rust that takes time to get used to, the idea that when I'm mutating data, nobody else should be reading or writing it. That's a really powerful concept that makes programs more reliable if you follow that structure. But the details of how we enforce it and how we figure out whether you are the only reader or writer and the and mute system, that's sort of accidental, and that's where we can make a lot of improvements. So we want to keep this core borrow checking check, but we want to make it more flexible and more capable, right? And as it happens, well, this particular function says, let me back up one step. It takes in an and mute to a vector. So it's saying I'm giving you a reference to a vector, and it gives back a reference to some string in that vector. That's what the signature means. And this is kind of a Rust convention. If you take in an and mute and you return an and mute, it must have come from the thing that you were given. So there's actually a more explicit notation that we call a lifetime notation, where you have these tick A note, these things. Not important, but the one part of this that is accidental, just to brave in that distinction, is that we allow you to elide those, and these details of how Rust is set up is accidental complexity. But the thing I really wanted to drive at here, and the thing that I think will change in Rust 2024, is that actually this code, as I showed it here, it seems pretty reasonable, but it doesn't actually build, because s, this variable s, is getting returned from the function. And the way that the Rust type system works now, that means that s, the variable s, has to be considered borrowed for the rest of the function. But if you look at where s came from, it came from the list. So that means that list is considered borrowed until the end of the function. And later on in the function, we go and mutate list. And the way that Rust guarantees unique access is when something is borrowed, we don't let you mutate it. So the fact that we're returning s winds up borrowing list all the way down here to the end of the function, and you get an error. Actually, we could try it out. Why not? I don't know if you're familiar with Play, but Play is the way that we let you run Rust code on the web. And you can see that if I try to run this, I get an error. Annoying. So there is a workaround. You can rewrite the code to move the borrow inside the if. It's not obvious. I'm not sure how you would know that this is the fix, and the code is worse. So before I mentioned that sometimes the type system can get in your way, this is one such example. Now, we've designed a new version of the borrow checker that we call Polonius, and it doesn't have this problem. It accepts this function, and I think we'll see that ship. I hope we'll see that ship in 2024 or before. And there's a lot of other examples like this. I don't have time to go into the details of them, but they're basically tweaks to the definition of Rust, and they kind of fall into two categories. In one category, like the one I just gave you, they take code that kind of should have worked, that if you sort of understand how Rust works, you expect it to work, but it doesn't because the compiler's too limited in some way or another, and just lifts those limitations. So more stuff just works. It's a win-win for everyone, right? And then there's this other section, which is actually growing the language so that things that you can't say, you now can. And I think maybe generic associated types, if some of you are familiar with that, would be an example where there are things that you wanted to be able to write, but you didn't have a way to express them in the language as it was. And so we're extending the language with constructs that will let you say the things you would like to say. All right, so the last thing I want to talk about is diagnostics and learning materials. I talked about how important error messages were for people, but here's a question for you. When is a Rust user most open to learning how Rust works? Maybe it's when they're reading the Rust book for the first time, or maybe it's later when they already kind of know how things work. You know, I think the answer is neither of these. I think the answer is when they hit a compiler error, because that's the point where they're having a problem and they would like to fix it, right? So they're open to learning whatever they have to learn to make it go away. And that's what we've always taken as our guiding philosophy, that compiler errors are our best teaching moment. But to that extent, you might wonder, what is the first thing a Rust user has to know to understand that error, right? To understand that error message and learn what it's trying to tell them. Is there some basic concepts they have to know? Maybe they have to know something about the Rust type system. Sometimes they have to know some of the vocabulary we're going to use, or ownership and borrowing. Well, even before that, there's something even more basic. They have to know English. All the compiler messages are in English today, and that's a big barrier for people who don't speak English that well. So one of the efforts we're undertaking, David Wood and the folks in the diagnostics working group are driving it, is this diagnostic translation effort, trying to give error messages in whatever language the user is actually using, right? So that they're that much more understandable, making Rust that much more accessible to people. But there's a side benefit too. As we take the error messages and instead of making them out of like hard-coded English strings in the source code, but actually building them out of metadata, we're able to build a lot more interesting tooling and a lot more stuff on top of the plain error messages we give today. So one such example that I'm pretty excited about is the ability to do custom errors and lints. So today, if you use the Diesel library, this is a library for interfacing with SQL. You can write these kind of neat scripts, like here it's deleting things where the ID is equal to 1, but there's actually a lot of sort of type checking that's happening in the background. Like for this to work, ID has to be a field that takes strings, but actually maybe ID is a number and not strings, right? So there's a type mismatch. There shouldn't have been quotes here. Well, what error do you get if you have id.equals 1? Well, today you get this crazy error. And the reason is that the Diesel's type system is being expressed through Rust traits and other mechanisms, and the compiler doesn't really understand it, so it can't give a custom error. So we'd like to allow Diesel to intercept this error and give something much prettier. And I think there's another level up, right? And this has been something we've talked about for a long time, but where I think it's a challenge, it's almost a messaging challenge to do it, but it would be really useful if we knew what errors people were hitting and what they did when they got those errors, so that we could analyze that data and say, oh, here's an error message that's really effective at, when people get this error, they're almost always, they can get their program back up and running in in one cycle or less, versus this other error. When people get this error, they get stuck. Or maybe they end up going in a loop where they fix the error, but then they get a different error, then they fix that error, but then they're back to the original error, and so they're kind of stuck. That indicates a real problem where either the error message is bad or something about that, part of the language is confusing, or they just don't get it. So it would be great if we could get that kind of data. Unfortunately, we have to be very careful about it because first of all, we would want to respect the user's privacy. We don't want to be able to identify individuals or anything. And we have to figure out, how do we manage data like that in an open source environment? I don't know. I don't think this is an easy problem. I just know that it would be really useful if we had the data. And I think it would help us direct our efforts and really make Rust error messages much better. So this is an area I think would be great to explore. Now, here's another question. For years, we've had this book available, our official Rust book. You can get it on the website or in printed form, and a lot of people love it. It's great. There's also other books from O'Reilly and Manning. But one question is, how do we know which sections of the book really work? Are there sections that are confusing, or things where people think they understand it, but they actually don't? So we've been doing, well, not we, Will Crichton, a postdoc at Brown University, has been asking this question and has started to run an experiment to figure it out. He's added inline quizzes into the Rust book to see how well you understand it. And the data, basically after you read a section, it asks you some questions and you can see, which then gives feedback. Is that section effective? Both to you, so you can go back and rework through it if you didn't actually understand it, and to the Rust book authors, right? And I think, as I said, to the language team. And in general, this is a cool area to integrate. So Will's doing that work, and there's a larger effort called Rust-edu, trying to bring people who are teaching Rust in university level and help develop a common curriculum for Rust and share tooling and tips and things like that. And part of what I'm most excited about with this effort, besides the idea that people will be able to learn Rust in their universities, is that we can start to get feedback from all these different people, right? Today, we mostly talk to developers who are using Rust to learn what kind of things are hard for them. But I would like to be talking to people who are teaching Rust, like teachers, and to the students who are learning it, and kind of taking all this data and trying to use it to really lower the Rust's learning curve and make it more accessible as much as we can. So that kind of covers some of the major things I wanted to talk about today. I want to leave you with one other point. I said that Rust is an open source project. And I think one of the biggest challenges for us is keeping that open source project, healthy, growing, and functional, right? So we've got, basically Rust is made possible by hundreds of longtime maintainers who work on it every day, and thousands of people who come in and do one-off contributions, pursue a particular feature or something like that. And some of them are paid for their time, and some of them are volunteers. And it's a great way to get new ideas, to get inspiration, but it's also a place that can be extremely tiring, and it can lead to burnout if people are working too hard and so forth, right? And so one of the things we're trying to figure out is, how can we really structure this open source org and always improve the way that we function? So I want to give a shout out to the Rust Foundation. I mentioned earlier, they launched in 2021. It's the legal entity that owns Rust, and its purpose is to support Rust's open source maintainers. They've been doing a number of efforts, like a community grants program, a cloud compute program where we offer developer desktops in the cloud to people working on Rust, so that some of them just have really slow laptops and it takes a long time to build the compiler. This can help with that. And then there's been a bunch of efforts within the org itself, right? So the foundation is kind of the structure on the side, and then we have the open source project, and they're they're not independent, but they are separated concepts. And so in the open source side, one of the things we've been doing is launching more dedicated teams. So if you're thinking of getting involved, this might be relevant to you. So one of them that I'm a part of is this types team. And the idea was that we noticed that in the compiler and the language level, there was an area which is like the details of the type system, but there really wasn't a lot of expertise, right? And not enough people really understood it. And so we're trying to form a team that just focuses on that area. So if you've ever liked to learn how a type checker works, for example, this would be the team for you. So I'm co-leading it along with Jack Huey, and we're just getting started now over this course of this year. You can come check us out in T-Types. But another thing, an idea I'm really excited about being pushed by Doc Jones is this idea of creating a dedicated onboarding pathway for people to become Rust contributors. Up until now, onboarding has been a kind of self-directed affair where people come, they find an issue they'd like to fix, they try to figure out how the compiler works. Sometimes we have mentoring instructions. Sometimes you can find someone to answer your questions on Zulip if you're bold enough to come and ask. And we have documentation like the Rust C Dev Guide, but it's still kind of a daunting task to really get started. And so the Rust Contributor New program promises to have a more structured experience where we have people sign up, we create a cohort, people work together, and you have some dedicated people promising to come and help you sort of learn how the tools work. And it's kind of like an internship, only different. So what I like about this is, I mentioned my goal early on with working on Rust is to help people build the things they want to build. And part of that is by using Rust, but part of that, I think, the Rust open source org developing Rust can itself be an empowering experience where you learn that indeed a compiler, it has this reputation as being a crazy complicated tool, and it can be, but also it's just a program like any other program, and you can learn to do it. And I think it's vital that we are really successful at getting more and more people, and especially people from all different parts of the world and all different backgrounds involved in Rust and in maintaining and implementing Rust if we want to ensure that we actually reach our goals in 2024. So that brings us to the end. I've given you a kind of survey over what's happening and some ideas of where I think we'll be next. I wanted to leave you with this picture that comes from RustConf a few years back. I've always thought it captured this spirit of what we're going for with Rust. This, a tool to build that crazy jetpack that you want and actually take off and fly. I think we've done amazingly well. I am so gratified to see that the work we've all put into Rust is started. People have really love it and are adopting it and making use of it. And I am super excited to see us keep working on it and making it even more accessible, right? Because I think our biggest challenge, as I said, is to reduce that hangover and lower the learning curve so that people can come into Rust as quickly as possible and start tinkering with whatever jetpack it is that they want to build. So thank you very much. I'll leave it here.
Hey, Niko, thanks a lot. Did you hear all the clapping?
No.
You didn't?
I heard it in my head.
Oh, man. All right. So before I let you go, you talked a lot about all these cool things that are going on with Rust. But wait, where'd you go?
Am I not here?
Come back.
I stopped sharing my screen. Perhaps that was a mistake.
I'll ask the question because we can hear you.
Okay.
You said all this stuff about Rust, but what's up with the crab? What's that? Where did that come from?
That's a good question. Ferris, you mean? Our
Ferris,
lovable mascot?
yes.
So actually, Rust's original logo was this, still our logo, was this bicycle wheel. And I don't remember when it was, but somebody in the community named Karen Tolva, I'm probably pronouncing it wrong, had the idea that we needed a better mascot, a more lovable mascot. And she was definitely right about that. And at the time, people were debating what to call someone who worked on Rust. There were a lot of names that came and went. But the one that seemed to be sticking was Rust Station, which is a lot like crustacean, which is the English word for a crab. So she made Ferris, and she released it to the public domain. And it's caught on and stuck ever since, and I think Ferris is great.
Yeah,
if you go to the website, I don't know if you've been to it. Hold on, I'm going to share my screen. I'm going to take
Rustations.net.
Privileges, yeah. Can you see this?
Yep. Yeah, we can see it.
Yeah, so if you haven't been to rustation.net, you should go. It's got not only the main crab, but a bunch of other, variations. I particularly like dancing Ferris over here. But, people have made all kinds of interesting Ferrises. So.
Cool. One last thing. Todo mundo aqui sabe o que é Popeye? Alguém aqui não sabe o que é Popeye? All right. So we were worried when you mentioned Popeye that people might not know what the hell it was. But apparently everybody knows, or people are ashamed of saying that they don't know.
Okay.
But it's all right. Niko, thanks a lot for being here remotely. Let's do this next time face to face. All right?
Yes.
And
that would be great.
appreciate the time that you took to share a little bit of your point of view. I want everybody here to clap one more time, and I'm going to let you go. All right? Thank you.
Thank you very much, everyone.